Okay. All right. So we're going to talk about electromotive force and internal resistance first. So we go by definition first, lah, right? Okay. The definition here, according to your textbook, electromotive force, I will use mainly based on your textbook. So you can open up your textbook, page 114, 114. Okay. So electromotive force, there are various sources, okay, such as electric generators, we have dynamos, batteries, accumulators, okay, even our power banks also have their own electromotive force in a way. So electromotive force is the energy transferred or work done by an electrical source to move one column of charge in a complete circuit. Okay, so the formula for electromotive force is the energy, right? Energy transferred or the work done per amount of charge flow. And you would notice one thing. This is very similar with V equals to W over Q. All right, the potential difference is the work done, all right, to move a column of charge from one point to another point. All right, so electromotive force is the work done by an electrical source to move one column of charge in a complete circuit. That's the difference from the definition of potential difference. Potential difference is the energy or transferred or the work done by a one column of charge to move from one point to another point. That's the definition for potential difference. But for electromotive force is from uh it's the work done, all right, to move one column of charge in a complete circuit. So the key here, electromotive force needs to be in a complete circuit. All right, so normally we write electromotive force as a cursive symbol like this. Okay, capital E is the energy transferred, or we can also use the work done. And Q, as previously, is the amount of charge flowing. SI unit for electromotive force is volt or joule per coulomb. Okay, so what does electromotive force looks like? Okay, I'm going to use this simulation over here. Wait, all right, so I have a battery over here. I'm going to show you the values. I'm not going to show the current. So we already understood previously that in order for current to flow, we need charge to flow. All right, so this charge is mainly the net charges flowing is electrons, negative charges. Okay, so over here, all right, what we have is I'm going to take a voltmeter. All right, this is a voltmeter saying how much voltage it is. So as you can see right now, the battery here is written as 9 volts. So when I connect this towards the battery, the voltmeter towards the battery, it's 9 volts. Okay, if let's just say for example, in an ideal case meaning means that I have a battery and then I have a light bulb over here. I connect this to a switch. I'm going to connect that to a switch over here. Okay. All right. So in a ideal situation, right, if the battery has 9 volts, we will assume that when we connect it to a power supply, all right, for example, if we connect it into a circuit, this light bulb, which is in series because it's the only component in the circuit, the potential difference across the light bulb is hold on, Omega, can someone send Maverick the link to the Google Meet? He just PM me for the link. Omega, someone please send it over to him. Alright, so over here what happens is that if I were to connect, right, my voltmeter across the light bulb, we should assume that it's going to be 9 volts also. Alright, let's see whether in real life case, alright, in ideal case, it is supposed to be 9 volts. Okay, ideal case means it is supposed to be 9 volts. But in a matter of fact, in real life situation, that always doesn't happen. All right. When the potential difference or the battery writes 9 volts, in real life, inside the battery, there are electrolytes. This electrolytes is the one that allows the battery to be positively and negatively charged at its respective terminals. But the electrolytes will also cause to have internal resistance inside the battery. All right. So when there's internal resistance across the battery, you would see that right now it's written 9 volts but 1.0 ohm. And right now, the potential difference across the light bulb dropped to 8.18 volts. So what actually happened? All right, this value, okay, I'm just going to screenshot this and bring it over to my PowerPoint. Have someone sent Maverick the link? Okay, so what we have here is this value of 9 volts is what's written on the battery. So this is known as electromotive force. All right, electromotive force, EMF. Okay, and then this value at the battery here is known as internal resistance. Okay, and the value of the potential difference across the light bulb, this one is obviously the potential difference that we learned previously. And this potential difference will obey what you known as the Ohm's law equation V equals to IR. All right, I'm using back that because that's how you guys has been memorizing it. But remember, Ohm's law is the potential difference is directly proportionate across the current, provided that the temperature and other physical condition are constant. Okay, so this value, let's go back to the simulation over there. Okay, this value here, you see how if I were to reduce the battery's resistance to very tiny, my voltmeter goes back to 9 volts. So this is the ideal case in most situations. We assume that when we buy a battery or when you buy a power bank, you buy a 10,000 mAh power bank. Okay, but in real life situation, you might not use that 10,000 mAh. You'll probably just use 9,900 mAh only. Same thing goes to battery. Same thing goes to pen drive. You buy a 32 gigabyte pen drive, but when you plug it into your laptop, right, it's not 32 gigabyte that you can put it in. It's only 31 point something gigabyte. Why? Because in that pen drive itself, it has its own software. All right, that when you reset the thing, the pen drive will auto reset everything back to the original setting. There's some storage over there. So for electricity, all right, electromotive force is the actual value. All right, I'm using something that you guys can understand now, but in terms of definition, please go back to your textbook. All right, so the electromotive force is the energy transferred or the work done by an electrical source to move one column of charge in a complete circuit. So how does it considered as a complete circuit in this situation? A complete circuit is whereby I'm just going to take this away. Like this. This is considered as a complete circuit already. Okay? So this is already assumed as a complete circuit. But if I were to connect this with the actual situation, there is internal resistance in the battery. Okay? So we have a switch over here. Again, back to our light bulb. Okay, this is also considered as a complete circuit. It's just that the external circuit out here, all right, this external circuit out here, it is a open circuit, no values. But the minute I close this circuit to make it a complete circuit, the light bulb is on. But as you can see right now, the voltmeter reading drops back again. So this is what we know as a voltage drop. Initially, the EMF is 9 volts, but then right now, when the external circuit is a complete circuit, the potential difference drop. Right, this value is 8.18. Okay, so the EMF value is 9 volts, and then when you close the circuit, the potential difference value, capital V, all right, becomes 8.18 volts. So what happened to the remaining 9.0 minus 8.18? What happened to the remaining 0.82 volts? This is known as the potential drop, all right, the voltage drop. So what happened to this? This amount of uh, voltage drop is used to overcome the internal resistance. Okay, so before I go into the formulas, let's go and clarify ourselves with some of the terms, definition, and also formulas regarding electromotive force. So I hope with the explanation of electromotive force just now, you all can understand already. Yeah. In a later, I will show you how do we identify whether is it an electromotive force question, or is it a ohmic conductors question where we need to use the series and parallel circuit. Okay, so let's see. Okay, electromotive force and potential difference, they have the same unit, but electromotive force differs from potential difference under certain circumstances, which means depending whether the circuit is open or not. All right, when the circuit is open, all right, the voltmeter reads the electromotive force. When the circuit is closed, all right, which means the circuit is on, the voltmeter will read the potential difference. That means the lower value. Okay, so like for example over here, now electromotive force, all right, initially we have the battery, okay, and then it's connected to a switch and then connected to a light bulb. Remember, for those of you who didn't come into the class previously, all right, a light bulb, okay, a light bulb is also similar to a resistor. All right, because light bulb has resistance as well. Inside the light bulb, there are wires, and that wire will act as a resistance, all right, to the circuit. So light bulb is similar to a resistor. So what happens here is that you have a battery connected to a switch, connected to a light bulb, and then we use a voltmeter to measure the value across the battery. Okay, so what happens here is that electromotive force, right? This voltmeter measures electromotive force when the switch is open. There's no current flowing in the circuit. Okay, let me just type that out. So voltmeter, since all of you are already using computers, so I'm going to just reduce the size. All right, voltmeter measures the electromotive force, EMF, when, okay, number one, the switch is off. Switch is off means the circuit is an open circuit. Open circuit means no current flowing. And then after that, what else? The light bulb is off, right? It's not lighting up. Okay, so the voltmeter measures the EMF when the switch is off, the circuit is open, there's no current flowing, the light bulb is not even lighting up. Okay, so what the voltmeter measures is the work done by an electrical source by the battery to move one column of charge in a complete circuit, just like this, at the top part only. So voltmeter, when the switch is open, all right, switch is off and open, circuit is open, okay, no current flowing in the circuit that has the light bulb, so light bulb is not on at all. So the voltmeter measures electromotive force. Okay, now but when the switch is closed, okay, so now the voltmeter measures the potential difference V. Okay, it measures the potential difference V when one, switch is on, or we consider as closed, complete circuit, the circuit is functioning, there is current flowing, okay, and then bulb lights up, okay. So this voltmeter right now measures the potential difference. Okay, now this voltmeter measures the potential difference, whereby the current flows in the circuit. Voltmeter reading in a closed circuit is the potential difference across the bulb. What does potential difference means? Potential difference is the work done to move one column of charge between 2 points. Which 2 points are they talking about? It will be from the positive towards the negative terminal. Okay, so it can also be the work done to move one column of charge in between the light bulb, because there's only one apparatus inside that. There's only one component, electrical component, that's inside that, and that's the light bulb. All right, voltmeter is a measuring instrument. So what happens here is that the voltmeter measures across the battery. It is also measuring across the light bulb. So what does this mean? How does it happen? So I'm going to show you again here. Okay, I'm going to move this up. So if I put my voltmeter across the battery, the voltmeter measures 8.18. So if I move this down towards the light bulb, it's still 8.18. Why? Because in this series circuit, there's only one electrical component, and that's the light bulb. Okay? So in series circuit, the potential difference is supposed to be adding up. But right now, there's only one battery, one source of battery, and then there's only one light bulb over there. So the potential difference across the battery is equivalent to the potential difference across the light bulb. That's why they have the same value. Okay, so that's the reason why in the textbook, the definition for potential difference is the work done to move one column of charge between 2 points. Okay, so up to here, are you guys clear with electromotive force and potential difference? If you are clear, you just put a OK at the chat box so that at least I know to proceed or not to proceed. Alright, see Harshini already responded. The rest all okay, Alright, good. Okay, so now let's proceed. Okay, why there's a difference? The main reason there's a difference between the value when the switch is open or the switch is closed is because of the battery's internal resistance. Alright, based on the activity just now, the simulations that I used just now, the value of the potential difference across the bulb is smaller by the EMF value of the dry cell. This indicates there is a voltage drop, there's a potential drop. So what causes the drop in the potential? Okay, I'm going to skip this activity. I'm just going to go to here. The main reason that it dropped is because inside the dry cell, there is a resistance caused by electrolyte in the dry cell. Okay, the internal resistance definition is the resistance caused by the electrolyte in the dry cell. So please remember, if in case this comes out in your trials or your SPM, make sure you spell electrolyte correctly. You give me the wrong spelling, then that's it lor. Okay, wrong already for definition. So the SI unit for internal resistance is ohm, same unit as external resistance. The internal resistance is caused by two things. Number one, loss of energy in terms of heat in the dry cell, as work has to be done to move one column of charge against the resistance within the dry cell, which means that because there are electrolytes inside the battery, so when the charge need to move internally inside the battery, they have to overcome the electrolyte, right? Because the electrolyte causes resistance. Remember, the main reason there is resistance is because of there are particles, atoms inside the metal or inside the battery. So in this case, when inside the battery there's electrolyte chemicals, meaning means there are other particles in there. So when you want to move one column of charge, electrons, let's say, from one end of the battery to the other end of the battery, it has to go through all these chemical electrolytes. So when it have to go through all these electrolytes, it is a resistance. So they will lose heat, right? That one column of charge will lose energy in terms of heat, not lose heat, sorry. It will lose energy in terms of heat. That's why sometimes when you touch your power bank, you feel hot. Or when you do certain stuff and you go and touch the battery feels hot. Why? Because the internal resistance inside the battery is quite high. Okay. Number two, second cause of internal resistance is the potential difference across the dry cell terminal to be less than the EMF when the current flows in a complete circuit. Meaning means that inside here, all right, when the current flows in a complete circuit outside, the potential difference across the dry cell drops down, right? The voltage drop just now that was mentioned. Okay, but for me, normally when they ask what is the cause of internal resistance, it's sufficient enough to mention the first statement here. All right, it's sufficient enough to mention this first statement. Okay, so the second statement, to me also sometimes it's a bit confusing lah. So that's why I've normally memorized the internal resistance. It's due to the energy loss in terms of heat when going against the electrolyte. Okay, so I've been memorizing that from last time already. Okay, so voltage drop. Now this is the formula over there. So I'm gonna show you guys how did this value comes up from. Okay, so first thing first, how do we identify whether it is a circuit that uses the series and parallel formula whereby we need to use V equals to IR, and when do we need to use the EMF? Okay, so very simple for me. Number one is throughout the question, you would see the question saying electromotive force. All right, you would see the word electromotive force. You would see the word internal resistance. Next is in the question, they will put a battery. All right, if there's a circuit, let's just say a resistor here and then another resistor here. Okay, but then normally in a series and parallel circuit, they will just write 9 volts. If they just write 9 volts and in the written sentences they didn't mention electromotive force, they didn't mention internal resistance, then you solve this question based on series and parallel and V equals to IR. But if above the battery suddenly you see this value, 1.0 ohm, 0.2 ohm, 0.5 ohm, a very small value of resistance is above that. This shows that this is internal resistance. The internal resistance, we use small r. The resistor and the light bulb outside, we use capital R. So internal resistance, small r. The outside resistance, I call it as external resistance. All right, the one that we need to use V equals to IR to solve it. Okay, so another method for us to identify its electromotive force and internal resistance is that there is a voltmeter across the battery. If there's a voltmeter across the battery and the question says when the switch is open, the voltmeter reading shows 9.0 volts. When the switch is closed, voltmeter reading shows 8.5 volts. Then that is a question of electromotive force and internal resistance. Okay, if they didn't mention this thing, they didn't in the question, they didn't mention EMF, they didn't mention internal resistance, the voltmeter is not across the battery but across, let's just say across the external resistor, and they didn't show this 1.0 ohm above the battery, then that one we use back series and parallel with V equals to IR. Okay, but if the minute electromotive force, internal resistance, then you have to use the internal resistance formula. Okay, so now how did the formula come out from? Okay, so I'm just going to show you very quickly. Now, another method that I used to see is that beside the battery, they draw a resistor, and then obviously there's a switch, and then there's a resistor here. This resistor can be one resistor, it can be two, it can be three, it can be four. All right, normally they don't give five, lah, okay? Now, and then they draw the shape of a battery. This also shows that it's an internal resistance. All right, when they draw a battery, all right, the shape of the battery, and then there's a resistor either cross or a square or rectangular inside there, this is also considered as an internal resistance question. Now, okay, I'm going to show you how does the formula comes out from. Now, so over here, battery, sorry, switch. Then we have the battery. I'm just going to simplify my teaching by putting one resistor here only. And then there's an internal resistance inside. Okay, so this is internal resistance R. I'm just going to put 1 ohm. And then my EMF is 9.0 volts. My external resistance is 10 ohm. Okay, so what happens here is, okay, if you look at this circuit, can you please tell me, ignoring the fact that this is internal resistance, does this circuit, if I were to close this switch, this circuit is a series circuit or parallel circuit? Is this circuit a series or parallel circuit? Answer at the chat box. Does this look like series or parallel to you guys? Hi, the rest of the 30 students is not missing, right? Thank you for responding, Lester. Thank you, Isha. Thank you to the rest who responded. Okay, now, so this is a series circuit. So in a series circuit, okay, we were talking about electromotive force and potential difference. Okay, so in a series circuit, V I R. Okay, so I is the same for series, V is the same for parallel. This is summation, 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 summation. Okay, V I series R parallel 1 over R. Okay, so because this is a series circuit, the potential difference across the whole circuit is summation, which means this is electromotive force. All right, here across this part, we know it's the potential difference V, capital V. All right, because we measured it in the simulation just now. 8.18 is the potential difference V. So, but there is a internal resistance over here. Okay, there's a value of internal resistance over here. So what happened here is the EMF value of 9 volts is equals to the external potential difference, capital V, plus with the voltage drop. Okay, so this voltage drop, you don't have to copy this, all right, this working, you just need to understand, don't copy it. So electromotive force plus the external potential difference plus the voltage drop. So the external potential difference uses this equation, V equals to IR. So capital I, capital R, plus this voltage drop, it will be capital I also. Why? Because this is a series circuit. In series circuit, the current is the same, which means that, okay, which means that the current that comes out from the power supply is the same current that goes through the internal resistor, is the same current that enters the internal resistor. So that's why it's capital I, small r. All right. So EMF formula is the potential difference plus capital IR. This is how they got the formula. All right. Because it's a series circuit, ma. All right. So this is the first formula, and that is what they show here. Okay, the voltage drop is EMF minus V. If you rearrange this equation, capital IR equals to EMF minus V. If you rearrange this equation, IR plus V equals EMF. EMF equals to V plus IR. See? It's the same formula that I did over here. It's just that I use another method to introduce out the EMF. Okay? So EMF, remember this potential difference uses capital IR plus I small r. This is I total, R total, the effective resistance in the circuit. So if let's just say EMF question, I'm simplifying stuff. There is a combination like this. Okay? There's a internal resistance of 1 ohm here. EMF value 9 volts. Okay? If you want to solve a question example like this, you have to turn all this external resistance into a single equivalent resistance of capital R. EMF 9, small r 1.0 ohm. Then only you can use this formula. Okay? Why? Because there are 1, 2, 3, 4, 4 external resistance on the circuit. When there's 4 external resistance in the circuit, your formula for potential difference, which is capital I, capital R, this capital R represents the effective resistance for series and parallel circuit. So you need to convert this 4 external resistance into an equivalent resistance first, then only use the formula V equals to IR and answer putting it back into this equation. Okay, so this is one thing that you all have to be aware of, because students always get stuck when they see this capital V. They thought this potential difference is a fixed value. All right, but in a matter of fact, because there is other resistor in the external circuit, they've forgotten that this potential difference, this capital V, can come from this table as well. Okay, so I hope that clarifies. If I don't see any messages inside there, so I assume that you all understand. If you have, as usual, put the message over there. Okay, so that's one part of the EMF. All right, so according to the voltage drop in your textbook, page 118, okay, voltage drop is IR, right, equals to EMF minus by the potential difference. So the potential difference equals to negative IR plus EMF. This is just manipulating the equation that I have over here. So I'm going to write my EMF equals to potential difference plus the voltage drop, or EMF equals to capital I, capital R plus capital I small r. The current is the same. All right. Why the current is the same? Because this is a series circuit. So this I can be extracted out to be capital R plus small r, EMF. All right. You don't have to memorize all 3 equations. You can just manipulating them by understanding that this potential difference is actually IR. Okay, I capital R. That one I have to be aware of. So, and this current here is the same current that is here. That's why I can extract the current out to be capital R plus small r, depending on what the question wants. Okay, then let's look over here. What else? EMF is the electromotive force. Please learn how to write electromotive force. It's a cursive, it's a terbalik number 3. All right, it's the opposite of number 3. Because if you write like this in the exam for EMF, I'm going to give you a wrong. Okay? Because capital E stands for energy, stands for electric field strength. Okay? It does not stands for electromotive force. Electromotive force symbol is a reverse number 3. Okay? So I is the current, small r is the internal resistance of the dry cell, capital R is the external resistance. So I've already showed you guys how did I get this formula already just now. Up to here, are you guys okay? Any responses? No responses? Okay. All right. Good. Now, so normally in equation, all right, for physics in equation, remember EMF equals to capital V plus IR. All this must use their respective SI unit. All right, you must convert them to their respective SI unit before you use the equation. Okay, whatever formula in physics, remember you need to convert them back to their SI unit. Okay, unless um unless like for example centimeter and meter, you want to find wave speed, you can leave the wave speed as centimeter per second, can, no problem. My meaning of conversion is, for example, energy. Energy formula SI unit is joule. But when we deal with nuclear physics and quantum physics, they use electron volts. So when we want to use the equation of E equals to mc square, convert the electron volts back to joules first. Okay? So these are the things that you have to be aware of. Now, in physics formula, all right, especially when you see like this, what else do I see in this formula is I see a graph equation. I see a linear motion graph. Why? Because all to the power of 1. So normally in electricity, we always plot a graph of potential difference V across current I. All right, potential difference V across current I, value volts, and current is ampere. All right, so how am I going to plot this graph? I need to rearrange this equation into y equals to mx plus c. Why do I rearrange it using y equals to mx plus c? Because it's all to the power of 1. So it's a linear equation. So my y-axis is v, my x-axis is I. So I need to rearrange this equation again. So I let v as a subject, and then I throw the voltage drop to the other side. It will be EMF minus capital IR. My current is my x-axis, so I put here negative R I plus EMF. So when I compare it with my y equals to mx plus c, my y-axis is potential difference, correct? My x-axis is my current, correct? My gradient is negative r, which means that my graph is a negative gradient graph. Okay, and then I have a y-intercept here as EMF, which means my graph is going to be a negative gradient graph with a y-intercept here. This value here is my EMF value. My gradient value is negative r. Okay, so this is one other types of electromotive force question. Okay, electromotive force, either number one, they give you a circuit for you to calculate. The second one is they will ask you from the graph. So electromotive force got two types of question. All right, if you need to copy this down, you better copy down, don't just look at the textbook. Moral of the story, try not to screenshot so much. You screenshot, you don't really go back and copy back. Okay, are you done with the screenshot and everything? Okay, so I'm gonna explain a little bit that's remaining in the textbook first before doing an exercise, and then maybe we can cover electric energy and electric power as well. Okay, so here we go into the textbook after the graph. Okay, so after this particular graph, this activity again we skip. Now, alkaline batteries that uses potassium hydroxide electrolytes are twice as durable compared to the zinc carbon batteries. For your information, this is another part that is new in KSSM. Okay, the effects of the dry cells connected in series and parallel, because last time they don't even bother explaining this. So now that they put in again, as I mentioned in the Form 5 syllabus, whatever that KBSM don't have, KSSM have. You are the second batch of the SPM students, so they will try to ask things that last time don't have first. Okay, so alkaline batteries that uses potassium hydrolytes electrolytes are twice as durable compared to the zinc carbon batteries. That's why some Energizer lah, uh, Panasonic batteries lah, right? It depends on what electrolytes they use inside that. Different electrolytes causes internal resistance of the two batteries to be different. So apart from the electrolyte use, the arrangement of the dry cells also affects the effective internal resistance. You know, I read this sentence, suddenly it gave me one thought. The next time I need to use a double A battery, I need to make sure that I use the same brand. Because if I don't use the same brand, they have two different internal resistance, it might affect how we use our normally batteries we will use for our torchlight, right? Okay. So next time you better be aware of all this lah. Okay, not all double A batteries or triple A batteries are the same. The electrolytes makes a difference also. All right, because they have different internal resistance. Now the effect of dry cells connected in series and parallel circuit. When the dry cells are connected in series like this, okay, if they are connected in parallel, which means the same structure, you still can use back the table that we mentioned just now. Okay, this table down here. All right, series parallel V equals to IR. I is the same for series. Potential difference is the same for parallel. So we can actually use that back because if you can see over here, dry cell in series, the effective resistance, the effective internal resistance is the direct summation. So which means that's why it's R plus R plus R plus R. So it becomes 4R. Right? It uses back the V equals to IR also. It's just that when we want to calculate everything else, we need to use EMF equals to potential difference plus voltage drop. Okay, but here internally, we still can use our series and parallel circuit for resistance, current, and potential difference. If it's a dry cell arranged in parallel, all right, resistance in parallel is actually 1 over R. Because we are calculating internal resistance, so we use small r. So that would be 1 over R, small r effective internal resistance is 1 over R plus 1 over R plus 1 over R plus 1 over R. So that's 4 over R. Remember one thing. Whenever you calculate parallel, you are calculating 1 over the effective resistance. Make sure you inverse back that effective resistance. If you don't, equation betul, substitution betul, answer and the final unit is wrong. Why? You forgot to inverse this value. Okay, so please remember to inverse it when you are dealing with anything in parallel. Okay, so the total EMF in this situation is 4 EMF. Why? Because they are in series. So the total EMF is EMF plus EMF plus EMF plus EMF. So it will be 4 EMF. But when it is placed in series, the total EMF is only 1. Alright? Because it's the same. The effective potential difference across a component arranged in parallel, potential difference is the same. That's why the total EMF is just EMF alone. Okay? So what does this mean? Please do take note here. The arrangement of dry cell in series increases the effective EMF, while the arrangement in dry cell in parallel reduces the effective internal resistance. All right, so that is one sentence that you have to be aware of. Okay, I'm going to use this example in the textbook. Okay, I know there is working over there, but I'm going to show you guys how to answer this example. Right. Okay, so in this example, all right, figure 3.32 shows two circuits with dry cell arranged in series and parallel. All right, when you see series and parallel, don't jump straight that this is not the EMF question, because the next sentence says that it is given that the EMF of the dry cell is 1.5 volts and the internal resistance is 0.5 ohm. So very obvious in the question itself, it will show you and tell you that you need to use the electromotive force equation of EMF equals to potential difference plus the voltage drop. Okay, and there's the internal resistance here. So they say it's like compare the current flow in the two circuits. Okay, which arrangement of the dry cell gives a greater current? So let's see, arrangement of dry cell, this is next to each other. Okay, because the battery is next to each other, the effective EMF is 3 volts. All right, the effective EMF is 3 volts. The effective EMF over here would be only 1.5. Now, why do I know? How do I know? Because this is arranged in series and parallel, right? So I draw my table of series parallel V equals to I R. In series, current is the same. In parallel, potential difference is the same. The rest is summation. So series potential difference is a summation, parallel current is a summation. In series, the resistor is next to each other, so it's summation R. Parallel, it looks like a fraction, so that's 1 over capital R. So the EMF can use this thing also, whereby we substitute the EMF with the potential difference. So each dry cell has 1.5 volts, so the effective EMF here is 3 volts. The effective EMF here is 1.5 volts only. Why? Because this is in series. They are the same. Okay? So compare the current flow in the two circuits. Because this has greater potential difference compared to this one, therefore, my answer would be the current flow. Okay, I need to do one thing. If this is a structure question, if this is the essay question, please remember to label. You don't label, I don't know what you're doing, I cannot give you mark. Even though I know you're doing this question. The current flow in the which circuit? Okay, circuit A. A is higher, is more, alright, than circuit B. Okay. So cross check. I thought they said compare only. Why they go and give the answer leh? Now I'm sure some of you will be answering in your head right now. When do you calculate and when you don't calculate? I guess that's in your head, right? Normally when we say compare the current flow, technically we just mention which is higher and which is lower, unless they ask us to calculate. So based on the textbook, they don't follow the SPM syllabus, SPM examination style already like that. Okay, because they directly go and calculate the thing. In exam, if when we see the word compare, we just compare in terms of words. We don't even do the calculation out. Okay, so if really have to do the calculation, fine, I'll show you the calculation as well. Okay, so how am I going to compare? How am I going to do this calculation? Okay, so I will have to use EMF equals to the potential difference plus IR. All right, so for circuit A, my EMF equals to the potential difference. I'm going to open capital I and capital R. Reason why is because we want to find the current, okay, plus I small r. Here, the current is extracted out, and that's EMF. So when I want to find the current, it would be EMF over capital R plus small r. So for the first circuit, the internal resistance are actually next to each other. So current equals to EMF, which is 3, all right, over capital R is 10 plus the small r here is 0.5 plus 0.5, that will be 1. Okay, so 3 divided by 11, I get 0.273 ampere. Okay, so cross check is 0.27. Can lah. Okay, so that is for my circuit A. My circuit B, because I have this equation already, so I'm directly going to use the same equation. I equals to EMF over capital R plus small r. But I have one problem because this internal resistance are parallel. Okay, so I cannot directly use this equation. I need to find the internal resistance. So how am I going to find the effective internal resistance? 1 over small re, because it's 1 over r, equals to 1 over r small r plus 1 over small r, 1 over 0.5 plus 1 over 0.5. That will be 2 over 0.5. Remember, this is 1 over r effective. So my effective internal resistance is 0.5 divided by 2, 0.25 ohm. Okay, remember, please remember to inverse this back. Okay, then only we can calculate the current. I equals to EMF over capital R plus small r, whereby this small r is the effective resistance. So that would be 1.5 over capital R, which is 10, plus 0.25. So 1.5 divided by 10 plus 0.25. My answer is 0.146 ampere. Mana pergi? 0.1463. Alright. So from the other day, Puan Liao's technique menjawab, she did mention the number of decimals is around 2 or 3 decimal places is acceptable. Okay, so that's why my answer just now was the current flowing in A is higher than current flowing in circuit B. So from my calculation, it does prove that it's correct already. Okay, so which arrangement of dry cell gives a greater current? So obviously the answer would be, okay, so I'm just going to draft my answer even though I know the textbook other answer. So for part 2, okay, dry cell arranged in series gives a greater current because, all right, because number one, what I can say is that the internal resistance is higher. Internal resistance is higher. Wait, the answer would be because the effective EMF is higher. Can you leave the answer just writing EMF? Yes, boleh. You don't have to spell out electromotive force. You can just write EMF. Okay? So if the circuit in figure 3.32 is replaced with 3 dry cells in parallel, okay, which means here, all right, it is connected to 3 dry cells in parallel, calculate the current. Let's see. Do you want me to finish explaining this or do you want me to proceed? I'm just curious. You want me to finish explaining the example or you want me to proceed explaining the rest of the conceptual part? Knock knock. Don't tell me anything up to me. Your exam is tomorrow, so you'll decide. Mingyu said concept. The rest, no response. So shall I follow just what Mingyu said? Okay. So if that's the case, then I'm gonna continue on lah, huh? Okay. So here also you have to be alert, alright, because this is something new again. Now, two types of vehicles using the electric power in the market right now. We have two types of vehicles, electrical cars, right? I'm sure some of your family cars are hybrid cars or they are electric vehicles, EV cars. Now, what is the difference? Electric vehicle, all right? Please do take note. This textbook is based up until, if I'm not wrong, 2019. So from 2019 until right now, 2022, there might be some changes in the actual situation, but in exam, SPM, we still need to refer back to the textbook, okay? So electric vehicle uses 100% electricity power using rechargeable batteries to supply energy to electric motors. So the commonly used batteries are lithium ion or NIMH batteries. Okay, the battery voltage range requires from 300 to 800 voltage. So for electric car, normally that's why you will see smart cars, so-called, they mention it as smart cars, they are actually electric vehicles. It is connected to the battery, whereby they will charge the battery and the battery will provide electrical energy to the electric motor at the engine there. But for hybrid cars, if I'm not wrong, is around 5 to 7 years ago they introduced it in Malaysia. Hybrid cars is a mixture of electricity and also petrol. Okay, so 25 to 40% of the power is supplied by rechargeable batteries, and the remaining is actually by fossil fuels such as petrols. So the battery voltage range is from 100 to 200 volts. So you can see the difference between the battery voltage. Okay, and over here we will have a petrol tank, and then at the same timing they have a battery inside there. And after, just like your power bank, right, if you would have known one thing, power banks, our normal power banks that we use, it has a lifetime, it can probably charge like for around 200 to 300 times full charge. Okay, so same thing goes to these electric vehicles and also hybrid cars. The batteries inside there also, they have their own lifetime. So when they finish almost ending their lifetime already, the owner of the cars will definitely have to bring the cars to change the battery. Right, they did raise issues about what happens when they change this battery. How are you going to dispose all these electric vehicle batteries, because they are chemicals. All right, so that is one debate that they had when they tried to commercialize the electric vehicles previously. Okay, let's see. This one, I think you guys can read it by yourself. Not much of a problem. You see, they did introduce solar cells, and the fact that solar cells is also in quantum physics in order to generate electricity. Then from the solar energy, converting it to electricity, and then they convert back into this chapter in electricity. Okay, so we're gonna go into electrical energy right now. All right. I'm not going to take much of a rest. I'm just going to direct, since tomorrow's exam. I want to let you guys to quickly finish up and then we'll go back and revise whatever you want. Go back after the lessons okay. So electrical energy here, all right, based on the formula of potential difference. This is the formula that we initially have in the beginning of the chapter. Okay, based on the formula of potential difference, V equals to the electrical energy over the amount of charge. Okay, my pointer. All right, we have V equals to the work done per unit charge, or we also have W over Q. Please do to take note, energy and work done can be interchanged. I repeat, energy symbol and work done symbol can be interchanged. Why? Because in order to do work, you are actually taking one type of energy to become another type of energy. So, and another thing, thing, if you would have noticed, both energy and work has the same unit, SI unit. Both of it is also joules, right? Because in order to do work, you need energy. Okay, so that is one thing that I need you guys to be aware of. I'm not talking about electrical energy only. It can be the forces and motion as well. So potential difference is the energy over a column of charge. So when I rearrange this, it can be E equals to V over Q. Okay, so this is the first formula for electrical energy. Do take note, be aware over here, unless you want to go and memorize 4 to 5 formulas of electrical energy. And then after that, we learn that current is the rate of charge flowing. All right, this is the formula for current, rate of charge flowing. So when I rearrange this, I memorize it as Q equals to IT. Okay, so this is what we have already memorized previously. So electrical energy here, okay, equals to VQ. So I am going to make this disappear. All right, first electrical energy formula is E equals to VQ. All right, and because Q equals to IT, when I substitute Q equals to IT into this equation, I get electrical energy equals to VIT. This is the second equation for electrical energy. Okay, then next, what am I going to play? I'm going to play around with the formula of V equals to IR. All right, I substitute V equals to IR into this equation. I get V equals to I square RT. Okay, and then if I were to substitute, this is the third one. If I were to substitute I equals to V over R, that means I rearrange this equation. All right, I substitute I into this equation, I will get E equals to V square T over R. So I have 4 equations for electrical energy. So you'll be thinking, which equation am I supposed to use for what? Okay, if they give you charge, then obviously it's the first one. Okay, then depending on what the equation give you, you substitute using whichever equation it is. So what am I trying to show you here is because this formula is obviously given. All right, V equals to IR is definitely already there inside the list of equation. Q equals to IT is also inside the list of equation. But VE equals to VIT, E equals to I square RT, E equals to V square over V square T over R, it might not be in the list of equation all the time. So you have to remember that you can substitute V equals to IR, Q equals to IT back into this first equation to get what you want. Okay, so I hope this one you understand why Puan Leong suddenly give you so many equation. Because I only memorized 1, 2, and 3 equation. Then the rest of this, I substitute the values inside. What the question wants, I use which equation. That's it for me. Now, one tips. Okay, whenever you see R, whenever you see resistance, this is not exam tips. This is answering electrical energy tips. Whenever you see resistance, you have to understand. Electrical energy will be lost at the resistance. Why? Because the resistance will oppose the current flowing in the circuit. So when it opposes the current flowing in the circuit, it will create heat energy. All right. And sometimes, okay, in a light bulb, okay, in a light bulb, electrical energy is lost in the filament as heat energy and light energy. But then because the light bulb is supposed to light up, so that light energy, we don't consider it as energy loss. All right. But what I'm trying to say here is when the question asks you to calculate the energy loss in the circuit, always use the equation that has resistance. I repeat, when the question asks you to calculate the energy loss in the circuit, always use back the equation that has resistance. Why? Because resistance is where the energy is converted from electrical energy to heat energy and light energy. Okay, so always remember this. Now, once we are done with electrical energy, do you all still need to copy this? If you need to copy this, please kindly copy or screenshot. Closing in 5, 4, 3, 2, 1. Okay, so electrical power. Once we are done with electrical energy, we have to go to electrical power. And from the basic formula of power is rate of change of energy. So power equals to energy over time. So just now, we have 4 formulas for energy. Energy equals to QV. Energy equals to VIT. I memorized this as vitamin E. Number 3, energy equals to V square. Not V square, I square R. Okay, never mind. And the last one, energy equals to I square RT. Okay, so if I want to calculate the electrical power, all I have to do is just substitute this into here. All right, so how am I going to substitute? This one will be power equals to QV over T law. Then the second formula would be power, because this is a time down here so the time gets cancelled off, IV. 3, power equals to V square over R, the T get cancelled off. 4, power equals to I square R, the T get cancelled off again. So there you have it, electrical power. Okay, so I always do one thing. Whenever I can derive, I will derive out. That's how I can memorize the equation. All right, so I'm going back to the textbook again. Okay, what is the relationship between power, voltage, and current? Okay, whenever you see an electrical appliances, normally you will see 2 things. The voltage, okay, not 2 lah, 3. Voltage, the frequency, and also the potential, the power, right? Weird why it returns watt. 700 watt, okay? What does this actually means? Let's see, here. You see, a fluorescent lamp is labeled 240 volts. Sorry, 240 volts, 32 watts. What does this means? I noticed that they did not show you the meaning of this. They did over here. Okay. Let me type out in a sentence. What does this label means? Just in case if they come out in SPM. A fluorescent lamp is labeled this value. This means that the fluorescent lamp will use 32 joule of energy in 1 second if it is connected to a potential difference of 240 volts. This is what the label rating means. All right. How did I get 32 joules per 1 second? Because this is potential difference. This is power rating. Power is energy over time. So if it's 32 watts, it means 32 joules in 1 second. So that's how I converted this out. If it is connected to a potential difference of 240 volts. Volts. My watts and volts. Okay? So then the question might ask, how much current does a fluorescent lamp use? Okay? So how much the current will flow? So using the formula, because I have potential difference, I have power, I know there's only one formula with potential difference and current, and that is IV. Okay? So in order to find the current that flows through the fluorescent lamp at optimum, it would be the power over the potential difference, 32 over 240. So that would use 0.133 ampere only. Alright? So the current will only use 0.133 ampere only. Okay? So that is what it meant. See? The current uses is actually 0.13 ampere. Okay? So let's see, power rating. Okay, LED light. There's one thing that last time ada, here tak ada. So I'm going to use my old notes already. Okay. Power rating. I already sent this out. To compare power rating and energy consumption of various electrical appliances. I remember this question came out like 3 to 4 years ago. They gave a picture of an electricity bill, and then they asked the students to calculate how much does that house need to pay. All right, this is something that I think I learned last time in KH. You guys would have learned it in RBT. Now, the larger the power rating in the electrical appliances, the more the energy is used every single second. Why? Because of the formula of power equals to energy over time. Okay, so the longer the usage time, the more the energy is being consumed. Okay, so in this case, what is kilowatt hour? In our TNB, bills, they always use kilowatt hour. Kilo is a prefix. Okay, kilowatt hour. Let me open up. Kilowatt hour. This is kilo times 10 to the power of 3. Watt hour. So watt is the unit for power, hour is the unit for time. So if you look at the formula that I wrote just now, power equals to energy over time. So when time goes up, energy equals to power multiplied by time. That's why the statement just now I had is the longer time you use, the more energy you are actually consuming. Because this is a directly proportional equation. Why? Because every electrical appliances, the power is actually the same. All right, the power that it will consume is the same. So if you use the electrical appliances for a longer period of time, the energy that you use will also be longer. Okay, so kilowatt hour is actually calculating the energy. Okay, so 1 kilowatt hour represents the amount of energy consumed in 1 hour by electrical appliances. And according to electrical companies, 1 kilowatt hour is 1 unit of energy. So if you look into the TNB bills, you will see all those how many units are. That 1 unit represents 1 kilowatt hour. Okay, so 1 kilowatt hour is using energy equals to power multiplied by time. So please be careful when you calculate this because it's supposed to be kilowatt and the unit is supposed to be in hour. All right, only for energy consumption in electrical appliances, the unit we use kilo, watt, and hour. We don't change it to watt second. Okay, we seldom change it to watt seconds. So this is what is mentioned here. I'm just giving you guys a brief explanation and all this. This is the traditional type of light bulb and also the LED light bulb. All right, at the very end, after using the same period of time, the old traditional light bulb actually uses 3 ringgit per month, but LED light bulb only use 0.942 ringgit per month. All right, so that's why um, we try to get people to change to LED light bulbs instead of using the traditional light bulbs. All right, LED light bulbs is definitely much more, in long term wise, it is much more cost saving, but to buy the LED light bulb is expensive. Okay, slightly, I think around 3 to 4 times more expensive. Okay, so let's see. Steps to reduce the household electrical energy uses. This one also, please be aware. Okay, few things that you need to know. These are the parts that normally when um, lower achievers and moderate achievers, when they are rushing time, for example, right now, um, they will skip this part because they think that they don't have enough time. They will skip this part. But this is the type of question that normally comes out in paper 2. All right, paper 2, section B and section C. All right, steps to reduce households electrical energy usage. So what are the steps? Close all the windows and doors when you're using the aircon. All right, so that the filter is clean and then it's cool and then the whole room cools down faster and more efficient. Switch off all the electrical appliances when they are not in use. This one, I think many people have this problem. Switching off the electrical appliances when they are not in use. You charge your handphone, all right? After finish charging your handphone, you just unplug the cable from your handphone and you just leave the power supply on. And for your information, whenever you leave the power supply on, you didn't switch it off, even though there's no power bank, there's no handphone, there's no tablet charging, electricity still continue on running. That's why your parents, whenever they want to pay the electricity bill, they'll start nagging you about you charging your phone lah. You don't switch off the power supply lah. This is the reason why. As long as the switch is still on, even if you unplug the power supply, but the switch is on, the electrical bill still continue running. Okay, washing machine use a full load, all right, and change to energy saving lamps like the LED lamps to reduce energy consumption. All right, so with this explanation, I think I am done. Any questions you want to ask me? Conceptual wise for this chapter, any questions you want to ask me? Ada? Tak ada? Okay. Since I see this, I might as well teach you guys this also. Okay. Fuse. Many people don't know what does a fuse used for. Okay. And many people also don't know how to choose a fuse. So to me, I think it's important that you guys know how to choose a fuse, especially the boys in this particular room also, because in the future you're going to be using electrical appliances at home. So you need to know what's a fuse, okay? Whether it's a fuse box or the fuse inside the power plug, all right? Fuse is actually a short piece of thin wire, which when current flows through, it will heat up, all right? It will overheat and melt if the current supplied is more than a certain value that it flows through. So if a short circuit develops in the appliances, like for example, just now in the afternoon, it was a very strong thunderstorm with lightning. Okay, my house already, as usual, normally when the lightning is very strong, my fuse box will actually trip. It's a good thing lah, because so that no extra current goes in. Now, a normal fuse is if a short circuit develops in the appliances, a current which is too strong, too high to flow, the fuse will melt. All right, this wire inside here will melt and break the circuit, because when it melts, the electrons cannot go through, the current cannot go through. So this prevents overheating of the wire that can cause a fire. So what happens here is that this fuse is normally located at the power plug. All right, it's a very small component over there. Sometimes electricians, when they go to your house, or when people actually trying to, normally the electrical engineers lah, okay, they will try to take away the fuse one. They will say, "Aya, this one never mind lah, no need one lah." But then it's very important. Why? Because if in case there's an extra high surge of current flowing in the house circuit, right? If your electrical appliances only need to use 5 ampere, but a sudden high surge of current or lightning allows 10 ampere of current to enter your house, whatever that you're using at that particular moment is going to explode, right? Because too high of a current is going to heat up, it's going to explode definitely. Okay, so the fuse main function is that when this 10 ampere comes in, the wire inside there will melt, and when it melts, it breaks the circuit, so current can no longer flow into the electrical appliances, like for example your laptop. All right, you try to imagine if a too high current flows in when you're using your laptop just now in the afternoon. If there's no fuse in the house, or there's no fuse in your power supplier, your laptop should have bye-bye already. Okay, so how do we know what kind of fuse to use? All right, we look at the electrical appliances example. These electrical appliances use 960 watts, 240 volts. So power is 960 watts, potential difference is 240 volts. So current equals to P equals to IV. So P over V, that would be 960 over 240. Okay, is already written over there, 4 ampere. Okay, so when you choose a fuse, all right, example, the fuse will be 3, 5, 8, 10, for example. All right, the fuse ampere is 3, 5, 8, 10 ampere. This 4 ampere is located between 3 and 5. Choose the one that is slightly more higher. All right, don't go choose 8, don't choose 10. Okay, so do you remember last time when I was explaining regarding the modification question? Even Puan Leong was mentioning, always choose 2 extreme end, high, low, long, short. Never choose the word moderate. Only for one situation, that's the fuse situation. And also for, obviously, for nuclear energy, alpha, beta, and gamma decay. Now, in case, in the terms of fuse, we need to choose slightly higher than the normal current. So the normal current is 4 ampere. So slightly higher, which means it's 5. You cannot choose 8. Because if you choose 8, the normal current uses 4 ampere. If the surge is 6 ampere, your handphone, if this is your handphone sudah terbakar already. All right, so it cannot be too high. It must be just slightly higher to protect the electrical devices from getting spoiled. Okay, so I hope that explaining regarding the fuse, that one you all can understand better. 3-pin plug, that one so long time never come out already lah, because they brought it down already. All right, so I think I am done regarding electricity. Any questions that you guys want to ask me? Last chance for you guys to ask me before I close the class. Tomorrow is going to be very, very difficult for you guys to find me. If you guys really want to find me, I am at the either chemistry, physics,